So in quick find, my trees are nice and flat, but it's really expensive to keep them flat. In quick union, it's cheap to let the trees just do whatever they want, but they can get too tall. So is there any way I can make choices based on something that's going to keep them flat enough without paying the expense of keeping it completely flat? We're going to look at two solutions. The first of these is to consider size, to say, okay, if I'm joining up two trees and they're different sizes, well, it doesn't make any sense to put the little one as the champion. So what we're going to do is record the weights of our trees. And whenever we union things together, we're always going to prefer the larger tree to be the champion. And so that's going to help keep things a bit smaller. Walking through the mechanics of the algorithm, it works like this. So when I'm going to union 4 and 3 together, I will again pick a champion arbitrarily. Note that the coding that the authors in the textbook used is slightly awkward here because it chose a different champion. So for their weighted code, they will always choose the first item as the champion in the case of a tie. But when there's not a tie, there's a canonical choice. It's not arbitrary. So when I'm trying to join 3 and 8, well, 3 is a lot bigger than 8. It's twice as big. So it's got to win. And that means the champion of 3 will be the new champion, regardless of its position, and we'll join them up as seen here. 6 and 5, again, arbitrary, and so 6 is going to win. 9 and 4, not arbitrary. So when we join 9 and 4 here, 4 has got to win. When we join 2 and 1, it's an arbitrary choice. 2 wins. 8 and 9 are already connected. When I join 5 and 0 here, well, 5 is the winner. That means 6, its champion, really is the winner. And then 7 and 2, obviously 2 will be the champion. And when I join 6 and 1, well, we have another tie. So in this case, I think, yes, 6 is going to be the champion. So 6 will get there. So note that what's happened here is that 2 just went under the 6. And there we are. So that's the example from the textbook. What does this do on my other examples? Let's suppose we go 0, 1, 0, 2, 0, 3. I think we got pretty good results before, and we still get good results. What happens in the really bad case, though, where I do the bad thing? That doesn't give me a bad thing. Look, I'm joining up these trees. Before I was getting something super tall. That doesn't happen here. And that's because the order of the two things doesn't matter. I'm picking the larger one. And so since 1 is the bigger one here, it wins. The only thing that changes is the initial value. So if I start with 0 and 1, well, initially there's a tie. And so how the tie gets broken will determine the winner. And in this case, the left hand is winning. So 0 ends up on top. And of course, if I have the same thing again and I'm joining 1 and 0, the order does matter initially. So 1 will become the winner, and then it'll come across on top. What happens if I join consecutive elements like 1, 0, then 2, 1, etc.? What happens? Well, it's going to do exactly the same thing. Again, because we're taking the larger side, and so it's always just going to win. And in fact, all of these things, it doesn't matter what order I put, it's always going to do the same thing. It's just a different champion, 0 or 1. What about for my halving situation? Well, in that case, and the reason I put this example in here, you can see that we have trees that are the same size. So when we have trees that are the same size, we always have a tie. And now we've got to just arbitrarily pick one to go beneath the other. And this is when the depth, if you like, will increase. The depth of our trees is going to increase when we have a tie. You can see that already when I start with the 16 separate trees and then start combining them pairwise. I go from a forest of depth 0 to a forest of depth 1. Now when I take my forest of depth 1 and I start pairwise joining them up, well, again, I don't have any bigger or smaller trees to deal with, so I'm forced to give them additional depth. So I'll end up with pairwise joining these, and now I have a forest of depth 2. And at this point, if I want to say join up 0 and 4, again, they have the same size. So there's nothing I can do. I've got to put one under the other. Same thing with 8 and 12. And you can see again, the depth has increased. So finally, I will increase the depth once more to get the final result. So this is actually the worst case that we can have in terms of the depth of the tree. And what's happening in the depth of the tree? Well, if you think about it, so if I have a tree of depth 0 here, that's just a single element, then that's one element, which is 2 to the 0th power. So that's what I've got. If I pair up two elements together, so here's 0 and 1 together, then I have two elements. I have a tree of depth 1, and now this is 2 to the 1, so 2 to the depth elements that I can fit in that tree. I can create many of those trees. Now if I take 4 elements and join them together in this worst case scenario, then what am I going to do? Well, I'm going to end up with a tree of depth 2. So note there's 2 links here to get from the lowest node to the highest node. That's depth 2. And there's in fact 4 nodes in this tree. So the depth again is, call it d. We have 2 to the d trees, or 2 squared. And that'll follow through again. If I go to 8 nodes, how many layers do I have? Well, we'll go from 4 nodes with 2 layers to 8 nodes with 3 layers. And if I want to go up to 16 nodes, how many layers do I have? I'll get 4. So you can see here, each time I double the number of nodes, I increase the depth of the worst case tree by 1. And what that means is that the depth of the worst case tree is the logarithm of the number of nodes. How likely are we to get some sort of logarithmic depth tree like this? Well, you can do some experiments. Here's one random experiment, and you can sort of see what the tree looks like. Not that deep. And running the performance numbers, you can see a dramatic improvement. So I am able to do much larger problem sizes here with much less time. Note that the union and the connected operations here take about the same amount of time, and that's not surprising because each of them have to do 2 lookups for the champion, and then they just do a constant amount of computation with that. You can run further experiments to sort of pick out what the average distance to the root is, and the authors of the textbook did this with 100 sites doing 88 union operations, and they ran the experiment a few times. And they found that the average distance to the root was about 5 in the quick union solution, and about 1.52 for the weighted union solution. And you can see the kinds of trees that you end up with. To implement weighted quick union, we need to do a little bit of extra work. Just to recall, here's the algorithm for quick find, where find was immediate and union had a loop. And when we went over to quick union, we moved the loop. So it left the union operation and moved over to find. And what we're going to do now is complicate union just a bit. So here, the choice of champion is arbitrary. We're always picking the right one. And what we need to do is make a more principled choice. So better choices, better outcomes. What are we going to do here? We're going to use some sort of size information. And I'm going to record that in an array called SZ. Initially, SZ will hold 1 for every element because each element is its own little tree of size 1. And what's going to happen when a winner takes a loser is that the winner is going to take all of the nodes from the loser. So the winner's size goes up. Note that the loser's size is not changed here, and that's because no one cares about the size of a loser, and we'll never look at it. So the only time we ever look at the size array is when we're comparing to previous champions, and we're picking the larger champion here. It's so dog-eat-dog. In any case, when I ran this experiment to make the slides, this is what I got. And you can see what I'm getting here is consistent with logarithmic growth. I'm running in operations. Each of them is taking logarithmic time. One can formally prove that the worst case running time for each call to union or find here is going to be logarithmic. And the way you do that is by arguing or formalizing the argument that I would just made intuitively when we were looking at the doubling of the tree. So if we're going to increase the depth of the tree, we can only do that when the trees are of equal size. So if the trees are not of equal size, we will not increase the depth. And that's what gives us the logarithmic result for the depth of the tree. Weighted quick union is not just a correct algorithm, it's a useful algorithm because we can perform these operations, union and connectivity, in logarithmic time. This is great. The algorithm can be made even a little bit faster. The big growth, the big performance increase we've had, we've already had it. But we can tweak this just a titch to get more performance. In order to do that, I'm going to first back out and look at a completely different approach to improving performance of quick union and quick find.